Today, we're taking a deep plunge into one of the most stressful, high-stakes areas of the modern energy market, short-term load forecasting.
Hmm.
Specifically, the challenge faced by retail energy providers, or REPs, when they need to predict demand for their customers, say, up to 2 weeks out.
Right.
This isn't just about reading a meter. This is about minimizing risk when, really, billions of dollars are on the line.
Exactly. For a huge traditional utility, forecasting is hard, sure, but they have a massive captive and, a relatively stable service area.
It's predictable.
For a retail provider, the difficulty is just magnified exponentially. We're talking about managing volumetric risk.
Yeah.
That's the difference between what you predicted you needed and what your customers actually consume.
And if you get that wrong,
If you get this wrong, you pay heavy penalties in the wholesale market. Even a 1 or 2% deviation during peak hours can mean millions in imbalance costs. So the AI and data strategies for these REPs have to be razor sharp.
So our mission today is to understand exactly why retail forecasting is so uniquely brutal and how they're using advanced AI tools to get that critical accuracy edge. Before we get into the roadblocks, let's start with the basics.
Okay.
What are the essential inputs that drive an electricity load prediction? What's on the, let's say, the core feature list?
It's a mix of the obvious and the subtle. You need a robust set of features, and the hierarchy of importance is generally pretty consistent. First, it's always weather.
Always.
We mean temperature, humidity, wind, and crucially, solar radiation. Load is fundamentally driven by thermodynamics and light.
Right. If it's hot, the AC kicks on. Simple as that.
Second, calendar effects.
Yeah.
Demand is completely different at 2 p.m. on a Tuesday versus 2 a.m. on a Saturday.
Of course.
So the hour of the day of the week, and whether it's a holiday are just non-negotiable inputs.
Okay, what's third?
Third, we have the changing nature of the grid itself, grid configuration. That means accounting for distributed generation, like rooftop solar, the impact of EV charging, and residential storage.
And fine.
And finally, the toughest input to wrangle. Consumer behavior patterns, the unpredictable human element.
Okay, so once we have that data, we need the toolkit to crunch it. When we look at modeling approaches, the source material shows a real spectrum of complexity, right?
Yeah.
All the way from basic statistics to deep learning.
Yeah, the toolkit is vast because no single model is perfect for every REP. You start with foundational statistical methods like ARIMA.
Okay.
These are excellent for capturing predictable seasonality and baseline trends, but they really struggle with surprises.
And then you move up in complexity.
Then you move into established machine learning techniques, things like random forest and XGBoost. These are tree-based models that excel at handling complex, nonlinear relationships between weather, calendar, and load.
And then there's the leading edge, deep learning. We hear terms like LSTMs, GRUs, and TCNs. For the non-data scientists out there, what's the fundamental difference between those traditional ML models and these deep learning architectures? Why do they matter more for load?
It's about memory and structure. XGBoost looks at features, independently. Deep learning models, particularly recurrent networks like LSTMs and GRUs, are designed to retain a memory of past events.
Ah, okay.
Since electricity consumption is highly dependent on what happened an hour ago or a week ago, these models are exceptional at learning sequential dependencies in time series data.
And TCNs?
TCNs, or temporal convolutional networks, are newer and often even faster. They look for patterns in larger time windows simultaneously, making them great at spotting, say, load ramps or drops.
So here's where we find the core insight. The best accuracy doesn't usually come from just one model. It comes from hybrid models.
Absolutely. The magic of a hybrid model is synergy. You use the robust statistical model to predict the predictable, reliable seasonal trend, the fact that July is always hotter than January.
A baseline.
And then you layer a neural network on top to handle all the complex, chaotic, nonlinear features and unexpected events. The statistical model stabilizes the forecast, and the neural network optimizes the fine-tuning.
That distinction makes perfect sense. Now let's talk workflow. The sources highlight that just using raw data isn't enough. You need feature engineering. You have to turn raw inputs into smarter, more useful features. What does that process look like?
It's all about creating context. The simplest engineered features are lag features. The load at time is highly correlated with the load at 2 Teralon, 1 hour prior, T2 to 24 yesterday, and T20 to 68 Toriel last week.
The recent past.
Exactly. You also calculate rolling averages to smooth out noise. But I'd say the most critical engineered feature for cooling demand is the temperature humidity index, or THI.
Tell us more about the THI. We hear that load is temperature driven, but why is that stickiness or humidity so vital?
Well, temperature alone doesn't capture how much the human body or a building feels the heat. Humidity prevents sweat from evaporating, making the air feel much hotter than the thermometer reads. The THI combines temperature and humidity into a single metric that better correlates with the operational status of air conditioning units. For an REP in a humid environment, using THI instead of just temperature can drastically cut down on forecasting error.
Smart. Once the model is built and trained, how do we know if it's any good? What are the standard measures of success?
Models are evaluated using standard metrics. We usually look at the root mean square error, RMSE, and the mean absolute error, MAE. These tell you the average magnitude of the error, usually in kilowatt hours.
But what do the business teams care about?
The one most cited by business teams is the mean absolute percentage error MAPE. That tells you, on average, what percentage off your prediction was. And these metrics are crucial because they ensure the daily rolling forecast is constantly monitored and updated.
Okay, let's pivot to the core challenge. Utilities forecast for a relatively predictable monolith. Retail providers forecast for a constantly shifting patchwork of customers. This introduces some specific and brutal roadblocks.
Yes, it does.
Let's dive into those key challenges, starting with the most immediate business risk: high customer churn.
Churn is the Achilles heel of any time series model built on historical averages. Imagine trying to predict the total spending of a restaurant whose 10 biggest regular customers switch to a competitor every 3 months.
Your history is worthless.
Your historical patterns are constantly being invalidated. When customers switch providers frequently, the load profile of your entire portfolio is unstable. It breaks and reforms, destroying the model's continuity.
So how do you mitigate that fundamental instability?
You can't stop people from switching, but you can forecast smarter. The solution is moving away from portfolio-only models and shifting focus to customer-level models wherever possible. You track load at the smallest increment.
And you have to be fast.
You must integrate real-time customer enrollment data directly into the forecasting platform. If a customer leaves or joins, the model needs to know that immediately. You then use adaptive rolling models that retrain daily or weekly to quickly absorb those changes.
That's a huge data management lift. Next up is the reality that weather is never certain. Weather sensitivity and uncertainty. How do you forecast load when the forecast for the driver of that load is itself uncertain?
That's the million-dollar question. You have to step beyond the single-point prediction. Instead of relying on one weather model saying it will be exactly 95 degrees, you use weather ensemble forecasts.
Which are?
They're predictions generated by multiple meteorological models, giving you a whole range of plausible temperature paths.
So you feed the load model not one temperature, but like 25 different temperature scenarios.
Exactly. And that naturally leads to the ultimate solution for risk management: probabilistic forecasting. Instead of the AI outputting a single number, the load will be 100 megawatts. It outputs a range of outcomes. We call them quantiles, like P90, P50, and P10.
I've seen those acronyms used a lot. Can you simplify what P90, P50, P10 means for the retailer?
Of course. P50 is your median forecast, the most likely outcome. P90 means there's a 90% probability that the actual load will be below this number.
So it's a high-end estimate.
A very high-end estimate. And P10 means there is a 10% probability the actual load will be below this number, or conversely, a 90% chance it will be higher.
And why is that so critical?
It transforms the forecast from a single guess into a quantifiable risk profile. The REP can now hedge based on the high-risk P90 scenario to avoid penalties, rather than just hedging on the P50 and, hoping for the best.
That helps manage the macro risk. Now let's tackle the micro volatility, portfolio granularity, and noise. Why is a small portfolio of retail customers harder to predict than a single large industrial plant?
Noise. Small residential or small business customers have erratic, noisy consumption patterns. A single home running the dryer at 7 p.m. matters very little to the overall grid, but when that noise aggregates across a smaller retail portfolio, it creates volatility that standard linear models just can't resolve.
So what's the solution for smoothing out that retail noise?
Clustering. You need to cluster customers by similar characteristics. Think of it like sorting laundry. You group customers with similar consumption levels, similar load shapes.
Like businesses versus homes.
Right, commercial users who peak in the day versus residential users who peak in the evening. You forecast each homogeneous cluster separately, and then you aggregate those results to get your total portfolio load. This isolates the noise and improves the signal quality for each group.
That segmentation leads us to a massive technical hurdle: demand response and behind-the-meter resources. Rooftop solar, home batteries. They directly reduce the power the REP sees. How do you predict a reduction you can't control?
This is a classic challenge. The meter only shows the net load, what the customer consumed, minus what their solar panels generated. To solve this, you have to use two-part models.
How does that work?
First, you model the underlying load, what the customer would have used if they had no solar. Then you model the BTM adjustments separately.
And how do you model that BTM part accurately?
You have to explicitly model solar PV output using inputs like irradiance and the known panel ratings of the customer. You also incorporate patterns for home storage discharge. The AI is essentially forecasting two things at once: what the customer wants to use and what they will generate themselves.
Okay, finally, we hit the operational reality, data quality problems. What happens if a retail provider relies on basic billing data, or if smart meters are missing intervals? The AI has no foundation, right?
This is often the biggest limiting factor for REPs. High-resolution smart meter data is the gold standard. But if it doesn't exist, they can't just give up. The most innovative solution here is synthetic consumer load reconstruction.
That sounds like digital alchemy. How do you reconstruct a detailed profile out of thin air?
It's not thin air. It's proxy data and established patterns.
Yeah.
When a retailer only has historical monthly consumption from a bill, these hybrid algorithms step in. They take that monthly number, combine it with generic load profile libraries.
Which are like templates for typical usage?
Exactly, a template for a summer weekday versus a winter weekend. Then they integrate estimated solar output. By combining these three sources, the algorithm constructs a synthetic demand profile, often at 5 to 60-minute resolution.
So you're reverse engineering the data you need using the few real anchor points you have. And for the data they do have, the solution is aggressive automated validation.
Absolutely essential. This means rigorous processes like missing value imputation, which intelligently fills data gaps, and anomaly detection. We use tools like the isolation forest algorithm.
What does the isolation forest do?
It's highly effective at spotting outliers, sudden, bizarre spikes or drops in consumption that likely indicate a faulty meter, not actual usage. By automatically detecting and smoothing these anomalies, the model trains on clean, reliable data.
Okay, let's step into the future. We fix the data and solve for the volatility of the present. How do we use AI to predict demand in hypothetical futures that historical data has just never covered?
This is the power of scenario AI forecasting. We acknowledge that the future will inevitably diverge from the past. Since you can't run a model on data that doesn't exist, this toolbox allows the REP to inject hypothetical scenarios without needing to write custom code.
Give us that extreme weather example again.
Let's say a retailer needs to understand their risk if the summer peaks consistently hit 10 degrees hotter than the historical maximum. They don't have load data for those conditions.
Right, it's never happened before.
So the AI uses its underlying models to automatically create synthetic historic demand and feature data that precisely matches that non-existent future scenario. It runs the model on this synthetic stress test data, giving the retailer a much clearer view of their risk exposure under future climate conditions.
And these scenarios aren't just about Mother Nature, are they? They're about market changes, too.
That's right. Scenarios can model expected step shifts. Say, a new manufacturing facility is scheduled to open next month, adding 10 milliW of load on a fixed date. The REP needs to incorporate that into the daily forecast well in advance.
That strategic link to costs is vital, especially when talking about peak load.
Peak load is where retailers hemorrhage cash if they get it wrong, because capacity charges are based on those few high-demand hours.
So you need special tools just for that.
We often implement peak-specific models designed just to predict those extreme hours, separate from the baseline forecast. We use that stress testing with high-temperature scenarios to predict the probability of peak demand, not just a single-point estimate.
Finally, let's talk structure. The AI needs to be flexible enough to aggregate data according to various business needs, not just overall portfolio volume.
Exactly. The intelligence platform must support dynamic aggregation and segmentation. This means the AI can aggregate load in real time based on any attribute the user needs, be it consumer types, specific tariffs, or how many customers have registered PV. This supports bottom-up forecasting.
And what's the complementary top-down forecasting view?
Top-down aggregates demand using network identifiers that are common in utility systems, like the GXP or the feeder. A GXP, or grid exit point, is where the main transmission enters the distribution network.
And that lets them double-check their work.
It allows the REP to ensure their total load forecast balances with the actual meter data they get from the transmission operator. It's an essential reconciliation check.
To bring this full circle, what strategic benefits are unlocked when a retailer achieves this level of forecasting accuracy?
The benefits touch every part of the business. Optimizing energy sourcing by purchasing power only when it's needed, much improved hedging strategies based on probabilistic risk, precise imbalance, volumetric risk analysis.
And it goes beyond just finance.
Oh yeah, even operational benefits,
Hmm.
like the ability to detect potential fraud or theft by flagging abnormal load behavior that deviates significantly from the model's prediction. It turns forecasting from a necessary chore into a critical competitive advantage.
What stands out here is the ability to connect the micro level, that synthetic load profile of a single customer, all the way to the macro level, reconciling that prediction against the regional GXP load. It's about building a fully integrated, risk-aware picture.
And that level of temporal resolution introduces a complexity we must always question. The source material mentions that while short-term forecasts are high resolution, long-term forecasts, those spanning 1 to 20 years, are typically done at monthly resolutions. These long-term projections are then scaled down to high-resolution 5 or 60-minute resolutions using standard profiles. This raises a crucial question for you to consider. When you take a general prediction made at a monthly scale for 2 decades in the future and mathematically force it into 5-minute increments, how much inherent uncertainty is layered into that minute-by-minute forecast? The temporal compression of risk is immense, and understanding that gap is the next strategic challenge for any retail provider.